Hello, my name is Hyunseok Lee. I'm a member of the KGSEA Math Circle, and today I'll be delivering my Math Circle Open School presentation on advanced statistics in sports analysis. Statistics and sports may seem like two very detached themes from surface value, and sure enough, that opinion was the norm for the first couple decades of organized professional sports, with simple statistics such as batting averages, points per game in basketball, let's say possession percentage in football or soccer, being the only real statistical values used to determine skill levels. But however, it soon became clear that these simple values were bound to miss certain contexts and are thus inadequate for deeper analysis of players and teams. So, finding a need for accuracy, there's been a constant longing for deeper, predictive, and decision-driving numbers to narrate outcomes. Moreover, as the sports market worldwide is dictated by massive amounts of earnings and cash, optimization has heavily been valued by executives and players throughout. So essentially, that thought process is pretty much the story of how the first seriously considered case of deep statistical analysis in sports came to be. That case was the start of sabermetrics, or SABR metrics, as some would call it, founded by statistician Bill James. Sabermetrics is the blanket term for sports analysis in baseball, or the development of advanced metrics based on baseball statistics that measure in-game activity. As talked about before, simple baseball stats may not tell the whole story. Take, for example, a .300 batting average may sound good and probably is good, but despite its wider usage in telling a shorter story of player success, it doesn't consider many other in-game factors or determinants, such as walks or situational values. Thus, the main aim for sabermetrics is to value every outcome with context. So perhaps the most commonly recognized metrics from the wider sabermetrics catalog is the WAR metric, which is an abbreviation for wins above replacement. So essentially, WAR attempts to summarize a player's total contributions to a team in one statistic. A player's WAR value can be summed up as the number of additional wins a team achieves by having that player compared to having a replacement level player. So this value sums up to a simple definition, but may go through much deeper calculations to the point where there still isn't a globally agreed upon calculation for it. So I'll try to put it in general steps. Firstly, you'll pick an attribute for a player. In this case, I'll say you choose batting, and you establish what replacement or replacement player is. So replacement, in theory, would be the average batting line of a freely obtainable AAA guy in baseball. So with the replacement guy, you fill an entire baseball team up with those replacement level players, and you run simulations for how many runs a team full of replacement guys would score in a year. Now you'd swap in your player and you'd simulate runs now, and the difference is how many batting runs over replacement our guy is worth. Now you'd you'd repeat for other averages or attributes such as base, running, and defense, and mash them all together, and now we have how many more runs our guy is worth than a replacement guy. For the last step, we know from other studies that team runs scored versus runs given up is good at predicting team wins. You solve for the number of runs you need to add to a team's win total for them to win one more game, and you take your guy's runs above replacement and divide by the number of runs per win, and then poof, you have the number of wins your guy is worth over a replacement player, hence your WAR value. Now, as I mentioned before, the exact formulae for the WAR calculations are still disputed, and different analytics sites and agencies will delve into complex, sometimes unwarranted, sophisticated equations. For example, Baseball Reference uses 6 components to calculate WAR for position players: batting runs, base running runs, runs added or lost due to grounding into double plays in double play situations, fielding runs, positional adjustment runs, and replacement level runs. So the term you see that for the equation you see on the top, which says P runs minus A runs, is your player runs minus your average player runs, and is essentially a sum of the first 5 values that I said, while the other term in the numerator, which is A runs minus R runs, or average player runs minus replacement player runs, is essentially forming from the last value. Now, after each of these components are computed and summed, runs are converted to wins by dividing a runs per win value determined using a Pythagorean expectation, which I'll talk about later. I did include other potential values or other potential equations that are used in measuring war values. But as I said, they're very sophisticated and more or less they come up with pretty similar results. So there isn't specifically a widely preferred method in the world of baseball. So you can see how war values determine players effectively. So looking at the chart on the left, war values can neatly categorize players and their skill levels. So for example, any player with a 6+ level war rating is an MVP caliber player. I'll put Shohei Ohtani as an example. I'm hoping everybody will know who Shohei Ohtani is. He had a 9.2 war rating last year, which is considered elite and one of the best rating seasons of all time. Um, and then you see how the graph below, which visualizes the spread of WAR based on a player's draft picks, you can see the correlation between their draft pick and their war rating. Typically, the higher their war rating, the higher their draft pick. Of course, this wouldn't be too accurate because a draft pick doesn't determine how good a player is going to be in the future. But essentially, it also does prove that WAR is a generally correct statistic to measure a player's potential success and their actual success. So next we'll go to OPS, which is a sabermetric baseball statistic calculated as the sum of a player's on-base percentage and their slugging percentage. OPS essentially stands for on-base plus slugging. So basically, the ability of a player both to get on base and to hit for power, two important offensive skills are what are represented here. This metric is a more direct alternative to tackle the problems of using simple metrics such as the aforementioned batting averages. On-base percentage essentially measures how often a hitter reaches base, whether through a hit, walk, or being hit by a pitch. Slugging percentage measures power by evaluating total bases reached per at bat. So if a player hits a double, which requires more power than a single, they reach two total bases rather than one. For OBP, or on base percentage, the numerator, which is represented as H plus BB plus HBP, or hits plus bases on balls plus times hit by pitch. That effectively means the number of trips to first base at least, while the denominator, which is AB plus BB plus SF plus HBP, which means at bats plus bases on balls plus sacrifice flies plus times hit by pitch, that effectively means just total plate appearances. The slugging averages has a much more simple equation, which is basically just the total number of bases based on the total number of at-bats. So moving on, one more sabermetric is the Pythagorean expectation, or what some people like to call the Pythagorean theorem for baseball. The Pythagorean expectation is a sports and analytics formula devised to estimate the percentage of games a baseball team should have won based on the number of runs they scored and allowed. Comparing a team's actual and Pythagorean winning percentage can be used to make predictions and evaluate which teams are overperforming and underperforming. And just to clear any confusion, the name comes from the formula's resemblance to the actual Pythagorean theorem. So empirically, this formula correlates fairly well with how baseball teams actually perform. However, statisticians, since the invention of this formula, found it to have a fairly routine error, generally about 2 or 3 games off. So, for example, I put the 2002 New York Yankees season, in which they scored 897 runs and allowed 697 runs. Now, according to that original formula, the Yankees should have finished with a win percentage of approximately .624. So that means based on a 162 game season, the 2002 Yankees should have finished 101-61. And they eventually ended up finishing 103-58, which does call for a slight error, but is generally proving of the fact that the Pythagorean expectation is expected to be highly accurate. So before we move on from baseball, I think it's important to note that sabermetrics and its invention has proven to be pivotal to the management of teams in modern baseball, as most strategies derive from statistical calculations to quantify player skill levels. The term Moneyball is used for the practice of using metrics to identify undervalued players and assign them to what ideally will become below market value contracts, This practice debuted in the efforts of small market teams to compete with the much greater resources of big market organizations. And the term itself, Moneyball, derives from specifically the 2002 Oakland Athletics and their fresh approach to utilizing sabermetrics. Um, the Oakland A's began seeking players who are undervalued in the market, that is, who are receiving lower salaries relative to their ability to contribute to winning, as measured by these advanced statistics. Now, by re-evaluating their strategy in this way, the 2002 Athletics, with a budget of $44 million for player salaries, were competitive with larger market teams such as the New York Yankees, whose payroll exceeded $125 million that season. Effectively, this approach brought the A's to the playoffs in 2002 and 2003. Now, to move on to how advanced statistics is used in any sport nowadays, we'll look at not baseball, basketball, which is my favorite sport. Basketball analytics is less widely known in terms of their usage in specific player evaluation, but one known analysis is the aforementioned Pythagorean expectation formula, which was modified to calculate the win-loss percentage for basketball. While less widely used, this statistic, despite being chosen with essentially a bashed power value, and of 13.91 and also being over 30 years old since its an initial finding, still holds up as a fairly accurate measure today with a not too high error margin. The analysis for the 1993 to 1994 season, which I've published the actual article for this right on the right side, and the 2014 to 25 season, they're both shown, and in both scenarios, they show teams not exceeding or missing their expectations by more than 5 games, or 5 or 6 games, which isn't really perfect, of course, but mostly are accurate within the 82 game slate. So analytics are used in strategy today in basketball and was an excessive driving force in changing the way basketball itself is played. So the 2010s Houston Rockets took a scoring approach through analytics, trying their hand in maximizing point efficiency per shot. So based on data, the most efficient scoring methods in basketball are three-pointers, shots at the rim, which are a high percentage and often draw fouls, and free throws, which are, of course, uncontested shots. So the Houston Rockets encouraged players to go for lots of three-point attempts, layups and dunks, and drawing fouls, and discouraged mid-range jumpers, which tend to have low efficiency per shot. So funnily enough, the general manager of the Houston Rockets at the time was the same guy to come up with the adjusted Pythagorean expectations. His name's Daryl Morey, and his approach to scoring, which was appropriately named Morey ball, became the norm for other teams as well. And now the NBA is dominated by sharpshooters who go for the exact routes that Morey ball recommended. Now, despite an analytics-based approach being lauded and widely picked up by sports leagues, there are always criticisms that note its limits. So first is its technical limits and capabilities, as not even the advanced stats pick up on the quote-unquote human elements of the game, whether they be injuries, fatigue, or weather in the case of outside sports. Also noted is the simple, unpredictable nature of sports in general. Yeah, unpredictability, because take, for example, the same Houston Rockets from before, who ended up losing in a crucial game in the 2018 playoffs, ironically by shooting 0 for 27 from the three-point line in the latter half of a very close game. So to summarize, I went through advanced statistics in basketball and baseball and why they're needed. I talked about sabermetrics and 3 specific measurement sabermetrics that are widely used in baseball today. And I talked about their applications in basketball, and then I talked about their limits, emphasizing that they, while widely utilized, are not perfect, and of course, isn't everything to analyzing players and team strategies in a game. For further research, I try to find real applications of any of these metrics to find out actual success stories and maybe come up with my own metrics and terms. Yes. That was my open school lecture. Thank you.